Ever wondered how long it would take for a can of beer to topple over? Due to quantum tunneling? The answer will blow your mind. Here we have our nice can of beer. Alright, so in problem 9.19, we have about how long would it take for a full can of beer at room temperature to topple over spontaneously? What a special word in this case. As a result of quantum tunneling. Hint: treat it as a uniform cylinder of mass m, radius big R, and height h. As the can tips, let x be the height of the center above its equilibrium position, which of course would be h over 2. The potential energy is mgx, and it topples over when x reaches the critical value of x not equal r squared plus h over 2 squared minus h over 2. Now, of course, in tipping, we have a tilted frame here. So we're looking at, halfway down the diagonal of the tilted reference. And we want to calculate the tunneling probability from equation 9.23 for E equals 0. Use equation 9.29 with the thermal energy, because again, if we're assuming that E equals 0 here, we need to have energy somewhere. That'll come from the thermal energy to estimate the velocity. Put in reasonable numbers and give your final answer in years. By the way, this is going to be wild. So why do we care? Well, this is going to give us straight insight into time scales and large numbers, which of course, dealing with the microscopic world and the macroscopic environment, there's a lot of particles and atoms and a whole host of things that have to deal with large numbers. Avogadro's number, you ran into that several times in your life. This is just on the same level except worse. So the challenge I have for you after this is to review and comment on the paper by Crandall from 1997, which you'll see later in the video. It is a wild exploration and definitely a mind-bending experience. Highly recommended. Don't forget, you can get the PDF. Just comment on it and I'll send you the link. Although in this video, everything's pretty much in the video itself, so you're not missing much. Not too much to worry about. That being said, if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee, no account required. So with that, let's jump in. Straight to stop number 1. Much like we've seen before, we are given, or we have to find the turning points. And thankfully, we're given the turning points in terms of the critical tipping value, where we have x not equal to square root of r squared, the radius, plus h over 2 squared. So this looks, of course, like the third leg of the triangle, the hypotenuse. Take away half of the height, so the center of mass. This is giving us half the diagonal if we were to draw this out. I kind of had a whiteboard sketch of this, but somehow lost it. And of course, with that, we're done with the critical point, so we don't have to worry about that for the integral. But now we have to find the momentum for this scenario, so let's do that. So straight to stop number 2. The momentum in this case is 2mv minus e. We've seen this before. Again, this is in the non-classical region, so we have E equals 0, and so V is greater than all that. So again, be aware of the regions and how that sets up the momentum, whether you need magnitude or to switch in the order, things like that. Because we're using gravitational potential, that's just mgx minus 0, so we're good. Combined terms, we see now we have an m squared. Now we can separate the radical into constant terms and a variable term. But with the m squared here, we can take that out front. So we're good to go there. And of course, we know we're going to have to integrate, so why not just put that to the 1/2 power and save ourselves some headache, thus completing the momentum. Now this brings us straight to stop 3, which is the tunneling factor. Of course, here we see the form of equation, I think 9.29, 9.23, one of the two. And when we plug everything in, we're good to go. We see that we got a bunch of constants here, so let's just bring them out front and finalize this integral. All right, cool. So with that, we have the constants out front, no big deal. We have the 1/2 power there, so add 1 to the power, divide by the new power. A fraction in the denominator means multiplying by the reciprocal. So we do that. Now we can evaluate the antiderivative variable part of this at the boundaries. And of course, with this being 0, the left-hand boundary goes away. So we're left with x0 to the 3/2 power with a bunch of constants. So we're good to go. But although we complete the tunneling factor, we still need to find some numerical things. And in this case, that would be to estimate the dimensions of a can of beer in order to actually plug in and find what the numerical tunneling expression is. So to do that, I'm using a product description seen here. And this came from a website that I did link in a PDF, as well as the mass of a beer, which I linked thanks to Reddit, because Reddit's awesome. But nonetheless, we use these descriptions and we're using a standard can that you would see from some of the big manufacturers. So with that, the standard 12-ounce can measures at a height of 122.22 plus or minus 0.38 millimeters. This is all from their website data table for these model numbers. And the diameter is about 66.1 millimeters, while the mass of a beer is typically 370 grams per 355 milliliters or 12 ounces. So once we get all the data from here, we are now stuck with the fact that these are not in proper units, so we need to convert them to the appropriate units, and we can do that next. Awesome. So mass, if we're using 370 grams, we know that in 1 kilogram there's 1,000 grams, so cancel. That's just a unit, that's just a decimal pushover. Same thing with height, 122 millimeters, 1,000 millimeters per meter. Cancel, good to go. Now, we know that for the diameter here, that means we have 2 times the radius. So if our diameter is in millimeters, convert, cancel. Now, in order to solve for r, we just divide this number by 2, indicate it here. So plug that in and we see what our radius is in terms of meters. So we got meters, kilograms, and now we're good to go. So the turning point numerically is we plug in our R, plug in our H over 2, we're good to go. Another H over 2, we're good to go. And we see that we get something very small in terms of meters, so 0.008378. Again, that's small, but whenever we plug it in all together, thanks to Planck's constant, this is going to be a big number. And so the tunneling factor numerically is now, well, we have 2 times the mass in kilograms over 3 times reduced Planck's constant. And notice that we're dividing by a negative 34, so that's going to turn this into a big old number. 2 times g, and then we have the x0 value here, of course kind of truncated to save space, but the calculator used all the values to the 3/2 power. And this brings us to 7.98 times 10 to the 30. That's a big old number. And remember that this tunneling factor goes inside an exponential. So that's going to be dramatically bigger. Okay, so just keep that in mind when looking at the scale of these things. Now, what this problem sets us up for is that we need the frequency of toppling attempts, which is just the velocity of the particle over where it can spread. So in this case, F equals V over 2R, which is the diameter, right? So if we're looking at the classical region and non-classical regions where it can topple, things like that, this is what the frequency turns to. And this is the same kind of argument the book used. But what we actually want is the product of the total number of attempts. So we have the frequency times the time. That's the total number of attempts at toppling that we have. Okay, and that the probability of the total number of attempts with the tunneling probability, if we want it to topple, the probability has to be 1. Okay, so this ensures it topples, where this is the probability of tunneling with all the tunneling attempts. So that makes sense. Now, from this, we plug in all the algebraic substitutions. We're good to go. But since we're highlighting for time, we divide over by v over 2r e to the negative 2 gamma. Dividing by a fraction means multiplying by the reciprocal. We're already a negative exponent, so double negative turns that to a positive, and we're good to go. All right, cool. So now before we can find the time, we still have one parameter left to find, which is the velocity. And in order to estimate that, we need to use the energies from the thermal effects. Okay. So, and we're told to use the thermal energy in the opening statement. And right here, we're going to denote the temperature as script T, as in to not be mistaken for the tunneling probability T. So that's the little notational difference. But clearly setting these two things equal, we see that 1/2 and 1/2 cancel. And if we divide by m, we get V isolated, but it's a square, so we need to take the square root. And that gives us KB, the Boltzmann constant, with the temperature over M. Now, we're also told that we should have this at room temperature. And according to a quick Google search, this turned out to be about 20 to 22 degrees Celsius. So we'll go with the higher one, even though it won't make any difference in the end. So that's about 295 degrees Kelvin whenever we convert it. We need to be in Kelvin for the Boltzmann constant. So check your units, make sure everything works out. A lot of thermal books put room temperature at about 300 Kelvin, so this is right in the ballpark. And from this, we can go ahead and find the tunneling time for this scenario. So we have T, which is 2R over V, so we plug V in algebraically and simplify, dividing by a fraction, multiply by the reciprocal, but you have to take the square root. So everything is good to go. That being said, you have 2R with the inverted square root and E. So now we need to find all of these constants and plug in the tunneling factor, which brings us to the numeric side of things, which will be interesting. So if we plug everything in, 2R, and now we have M, Boltzmann's constant, then the room temperature, and then clearly here we have 2 times the tunneling factor, which I said was huge already. Now you're putting that in an exponential. This is going to be brain hurt. Okay, so we see that all these constants, again, that negative 23 being dividing is going to lead to a big number here, even with the square root. Multiplying everything out gives us 6.2985 times 10 to the 8th times the exponential, which is 1.59 repeating times 10 to the 31. And this will not ever be computed in a calculator using something like Mathematica or Wolfram Alpha, something like that is going to have to be used. And what they do is convert this to a double exponentiated number because this number is so darn big. We see we have 10 to the 10th power, but this 10th power is to the 30th.8 power. And even dividing this by the amount of seconds into years to convert it, which is about 30, let me verify, 31.5 million seconds in 1 year, doesn't even dent this number because of how big it is. This is an absurdly large number, and I don't think it's going to happen anytime that the can is going to spontaneously tip over. This number is so darn big. Again, like we saw in the last question, the age of the universe is only about 1.38 times 10 to the 10 years. So just try to compare that this thing is a, 10 to the 29 bigger. It's just it's enormous. And by the way, trying to calculate this numerically in Python, the Python does not like this and will say that you have a divide by zero error somewhere in the computation, which means that you go to infinity. And it's just dramatically crazy and all things related. So that brings me up to the challenge of this problem that I gave you. Now that we have time, the challenge is look at this paper, the challenge of large numbers. Now, I think I'm just going to end up doing an article review on this because it really hurt my brain and I got real excited about this no matter how many number file videos or other YouTube videos I've seen on large numbers and how complex they are. This thing was a great insight, and that was done again in 1997. So, rereading this just really helps orient ourselves in the landscape of physics and math and what else is out there in the universe. Very, very cool paper, which I highly recommend. And if you're interested in joining a discussion about it, let me know because I'm definitely all here for it. There's lots to learn in this arena, and I want to learn more. Oh boy, that was a very fun problem that was not at all anything applicable to us, but helps to generate the perspective that we're missing when we're dealing in a microscopic system and we're trying to relate it to our everyday world. Beer can, soda can, energy drink, all of that could have been used the same way. And it's just amazing how different the worlds are. And then again, this is still zoomed in. If we zoom out on the astronomical level, those numbers are huge too. Okay, so it's really hard to perceive the relational uh, scales when you're dealing with the microscopic and the very macroscopic. It is really brain hurt, and it makes me real excited to look into more of it. And eventually we'll get into an astrophysics book too, because I just can't help myself. It is so darn amazing how scientists have created all of this, and the fact that we're even attempting to tie it all together gives me real pleasure and excitement to what the world can be. So, that being said, thank you for watching. I know I ramble a lot in excitement, I can't help myself. But that being said, again, massive thank you to all my supporters for making this possible. As everything grows, we can do more, and I can put more time into this and do more of the article reviews as we're tagging along. Because quite frankly, I think that that's the missing step between what the book does and what we saw in actuality. Just like that artificial problem with the quantum bouncing ball, how that was used in neutrons. Who would have thought that a seemingly artificial problem like that or this was actually applied? And without these papers, it's easy to lose track and just trying to get through another problem set. So I think that's very important. Books, notes, and other reference materials will be found below. If you have any questions, please feel free to reach out. Learning is all about trying to grasp the concepts in your own language. So more perspective is always better. If you want to support the channel more too, feel free to become a patron so you can have access to the discussions and all the other fun stuff, especially the one-on-one help now that the new semester is coming. Definitely love to help people achieve their goals. That being said, as always, thank you for watching, and until next time, stay curious.